In this video, we're going to solve equations to where the solutions contain complex or imaginary numbers, or at least have some imaginary components, so I, and or the equation itself has some imaginary components. In this case, for this equation, there's no imaginary components, but some of the equations we're going to solve will have imaginary numbers. And so this is really interesting because now that we know how to add, subtract, multiply, divide, take powers, and take roots of complex numbers, with that, there's a large array of equations that we will have no problem solving for all of the potential solutions throughout the entire complex plane, as well as, if you can have components with I anywhere in the equation, and that doesn't matter. We still know how to solve it. Now, it's not like we could work with any equation at this point. If there were logarithms involved or exponentials involved, we wouldn't know how to work with equations like that, but we'll learn that in complex analysis course. But still, being able to add, subtract, multiply, and divide and take powers and find roots is still a large amount of mathematical operations we're able to work with complex numbers. So, okay, let's solve this equation. For each of these equations, we want to solve for all solutions throughout the entire complex plane. So there's going to be X variables, and the idea is what are all of the solutions in the entire complex plane where you plug that in for X and it satisfies the equation. So we can start here by adding 1 to both sides, and we're left with X cubed is equal to 1. And so now for these equations, what we're going to do is, if there's a situation where we can take a root of both sides and to isolate the X, we're going to do that. Okay, now I've talked about this. This can be a little confusing working with radicals in the context of complex numbers. We don't want to be mixing radicals with complex numbers at this point. However, when it comes to taking roots of both sides of an equation, we're not really using a radical here in the same way that if we were solving for a theta and we had to introduce an inverse trig function to isolate the theta, we're really not. This really isn't an inverse sine function. It's in the sense that it restricts the output to one output. That's the whole thing about the radical, right? It's like it's a special case of a root where you're restricting it to one output. Well, we're not really doing that here, right? If we introduce the inverse sine, we're really thinking about the big picture question. What are all the angles? When you take their sine, you get root 2 over 2. And it's the same idea here. Since we introduce this radical, then we're really asking the question, what are all of the numbers? When you cube them, you get 1. Okay. Now, I mentioned, though, that you can take advantage of the radical if you want to, in the sense of if you're looking at an equation and you're saying the only solutions that are going to be specified are going to be just real numbers. So you're ignoring the I don't want to say the complex plane, but you're ignoring any imaginary components. You're just looking at real numbers. Well, in that case, what you can do is you can actually use the principal root symbol, and you can trust it across the board, with the only requirement being that if you take a fourth principal root of both sides, then apply the plus or minus. Like, you can kind of use that square root property even outside of square roots if you're restricting the outputs, the solutions, to be just real numbers. If you're allowing for complex solutions, then you don't want to do the plus or minus here, because that's not going to work. That plus or minus would only work with complex solutions. The square root property only works with this property. It wouldn't work if you had x to the fourth is equal to minus 1. You don't want to be doing this. You can't even take out an I here with an even root. So the idea is you can apply that plus or minus square root property if you're saying the outputs can't be, there's no complex outputs. And in that case, then, if that was the case, then like here, you'd say there's no solution, because there's no number when you square it, you get -2 if you're just thinking about all real numbers. And there's no number when you cube it that you get negative 16, so there's no real numbers. So you wouldn't even be having a case of an even root over a negative number. It would just be even roots over positive numbers. So that's how you would work with it. You could use radicals for the case of if you are solving equations and saying that the solutions could only be real numbers. But for the case where you're allowing any numbers, the solutions to be any number, or you've got equations that have i's in them, then you're viewing the radicals as just the same way you view inverse sine when you introduce it. That it doesn't really, this isn't really a radical, because we're not looking at this as like it's the principal cube root of 1. We're looking at this as what are all of the numbers when you cube them that you get 1. That's what we're looking at it as. So, well, how do we solve for those? Well, we know how to do that, right? It's just going to be, we come off to the side and say, we've got the complex number 1 plus 0i. Okay, now we want to find all of the cube roots of this complex number, just like we did in the previous video in this section. So we first put this in polar form. So the radius is going to be 1, and the angle is going to be 0. It's just a positive real number. Okay, so now we have it in polar form. We know that all 3 of the roots are going to have the same radius, which is the principal cube root of this radius. So this radius is 1. So the radius of each one of these is going to be 1. I'll just leave the 1 out since it's just 1. Okay, now the each of the angles, alpha, are going to be, so, oh no, this was 0. So each of the angles alpha is going to be, we first put this 0 degrees, the angle from the root in polar form, and then plus 360 or 2 pi times k. K is any positive or negative integer over 3 being the root that we're calculating. Here's the third root. But we put whatever the root is. Okay. Now, but the 3 alpha values are going to be for k is equal to 0, 1, and 2. And we stop at 2 because we got 3 values. If we had n is equal to 5, we'd stop at 1, 2, 3. We stop at 4. So we have 1, 2, 3, 4, 5 values. You stop at n minus 1. Okay. Now, so alpha 1 is with k is equal to 0. You've got 0 divided by 3 is just 0 degrees. We know they're going to be spaced 120 degrees apart. We've got 3 roots, so we just add 120. Okay, so let's see. We've got cosine of 0 degrees plus I sine of 0 degrees. We've got cosine of 120 plus I sine of 120. And we've got cosine of 240 plus I sine of 240. Okay. Let's put these in rectangular form. So, okay, cosine 0 is 1. And sine 0 is 0, so that's it. There's one of the roots, obviously, because 1 cubed is equal to 1. Okay, now 120 and 240, we can use the 30, 60, 90 triangle. So 1. Okay, so 120 is in the second quadrant with reference angle 60 degrees. So cosine of 120 is going to be minus 1/2. Sine of 120 is going to be root 3 over 2. Positive root 3 over 2. Okay. 240 is in the third quadrant, reference angle 60 degrees. So cosine of 240 is going to be minus 1 over 2. And then sine of 240 is going to be minus root 3 over 2. And there we go. There are the 3 solutions. If you cube any one of these, you're going to get 1, which means that if you plug it in here, you're going to get 1. 1 minus 1 is 0. Okay, here's an equation. You see, the equation itself contains an I, but this shouldn't scare us at all. We just treat I like it's any other number. So let's subtract I from both sides. And then, okay, take the cube root of both sides. And now, okay, we're not treating this like a principal cube root. We need to answer the question. Since we introduced this to solve the equation, we need to answer the question, what are all of the numbers that when you cube them, you get minus I? So there's going to be 3. The nth root of any number, any complex number, is going to have n roots. Okay, so this is 0 minus I, and that has radius 1 with angle 270, the negative vertical. Okay, so the radius of each of these is going to be 1. Now we've got, let's see, so alpha is going to be 270 plus okay, with k being equal to 0, 1, and 2. So alpha 1 is equal to 270 divided by 3 is 90. And then we know that they're going to be spaced 120 degrees apart. We still have a root 3 here. In the upcoming problems, we'll finally get away from just doing root 3 every time. So this is going to be 210, and then this is going to be 330. So we've got cosine 90 plus I sine 90. Then we've got cosine of 210 plus I sine of 210. Then we've got cosine of 330 plus I sine of 330. So we can convert these to rectangular. We can use the 30, 60, 90 triangle again. Usually you won't be able to use a reference triangle like this, but we do this to make it simpler. So 1, root 3, 2. So, okay. With 90 degrees, you've got cosine 90 is 0, sine 90 is 1. So this is just going to be I. Here you've got, let's see, 210 would be in the third quadrant, reference angle 30. So cosine 210 is going to be minus root 3 over 2. Sine of 210 is going to be minus 1 over 2. Okay, let's see. Fourth quadrant now, reference angle 30. That's going to be, cosine 330 is going to be positive root 3 over 2. And then minus 1/2 would be sine of 330. And there you go. Those are 3 solutions. So we can see, what is I cubed? Well, we know that's minus I, right? Well, minus I plus I is 0, you see? Okay, x cubed minus 8 is equal to 0. Add 8 to both sides. Now take the cube root of both sides. And if we were just considering real number solutions, this would just be 2. That's it. But we're thinking about what are all of the numbers and all of the complex plane, all of mathematics, that when you cube them, you get 8. So we've got 8 plus 0 I in polar form. That's cosine of 0 plus I sine of 0. Okay, so let's see. Radius of all of these is going to be 2. Okay, now let's see. The alphas, we've got 0 degrees plus, okay, over 3, with k being equal to 0, 1, and 2. So we got alpha 1 is equal to 120. Alpha 2 is going to be 240. Just keep adding 120. Alpha 3 is going to be 360. So 2 cosine of 120 plus I sine of 120, and then cosine of 240 plus I sine of 240, and then cosine of 360 plus I sine of 360. Okay, so we can use the 30, 60, 90 triangle again. Okay, 120 is in the second quadrant, reference angle 60. So let's see. Cosine 120 is going to be minus 1 over 2, so minus 1. Sine 60 is going to be, in the second quadrant, it's going to be root 3 over 2. So plus I root 3. Oh, wait, I didn't do this right. Hold up. This is, when k is equal to 0, you've got 0. So it's going to be 0, 120, 240. So, okay, well, we got this one. Okay, so this is going to be, the second is going to be 1 plus I root 3. That'll be, so cosine of 0, 120, okay. And then this is, so 2, yeah, just 2. 2 plus 0 I, and then 240, you're in the third quadrant, reference angle 60. So that's going to be the cosine of 60 in the third quadrant. You've got minus 1 over 2, and then sine 60 is going to be minus root 3 over 2. Oh, but you multiply by 2, so minus 1 minus root 3I, or I root 3. There we go. Okay, let's subtract 1 from both sides. Fourth root. So now we're asking for what are all of the numbers that when you take them to the fourth power, you get minus 1. Now, if we were just restricting this to real solutions, there'd be no solution to this because there's no real number. Whenever you take it to the fourth power, you're going to get minus 1. So there's no solution in that case. But with imaginary components, there are solutions. So we've got minus 1 plus 0I. Okay. Now, in polar form, that's going to be cosine of 180 plus I sine of 180. Okay. With radius 1, so the radius is going to be, for each of these, is the principal fourth root of 1 is just 1. So each of these is going to have radius 1. Now, the alphas, we're finally dealing with a root that's not 3. We're going to have 180 plus 360 times k, but it's going to be divided by 4. With k, the 4 values are going to be with k equals 0, 1, 2, and 3. Okay, so we can get alpha 1, plug in k is equal to 0. 180 divided by 4 is, that would be what, 45. Okay, we can keep plugging in 1, 2, 3, and 4, but we can just use the fact that since there's 4 roots spaced evenly around 360 degrees, we know they're going to be spaced 9 degrees apart. So we've got 135, and then 225, and then I think 315 should be, yeah. And there we go. So we've got, let's see, cosine 45 plus I sine 45 cosine 135 plus I sine 135. You've got cosine of 225 plus I sine of 225, and then you've got cosine of 315 plus I sine of 315. Now we can put these in rectangular form. So let's use the 45, 45, 90 triangle. 45, 45. So 1, 1, root 2. All right, first quadrant, well, that's easy. 1 over root 2, which would be root 2 over 2. So root 2 over 2 plus root 2 over 2i. Okay, in the second quadrant, reference angle 45 degrees, we'll have the cosine component is negative, or the horizontal component, so minus 1 over root 2, so minus root 2 over 2, and then plus root 2 over 2i. Okay, 225 is third quadrant, reference angle 45, so that's going to be both components are negative. Okay, now reference angle 45 degrees in the fourth quadrant, you've got, let's see, cosine is going to be positive and sine is going to be negative. And there you go. You take any one of these to the fourth power, you're going to get negative 1. Okay, let's add I to both sides. Okay, fourth root. So x is equal to, we're going to have, what are the 4 numbers in the complex plane that when you take them to the fourth power, you get I. So we're dealing with 0 plus I. In polar form, this is cosine of 90 plus I sine of 90. Okay, the radiuses of each of these, principal fourth root of 1, so they're all going to be 1. So we've got alpha is equal to 90 plus 360 times k all over 4. So alpha 1 is going to be, when k is equal to 0, 90 divided by 4 is what? Is 90 divisible by 4? No. So 22 and a half. Okay, alpha 2 is going to be, well, we know they're spaced 90 degrees apart, so we've got 112.5. Okay, another 90 degrees, we've got, let's see, so 22.5 plus 90 plus 90, 202.5. Okay, let's see. And then 292.5. All right, so we've got just cis 22.5, cis 112.5. Okay, now let's put these in rectangular form. Okay, so cosine of 22.5, sine of 22.5. So 0.92 plus 0.38i. Okay, now sine of, all right, minus 0.38 plus 0.92i. Okay. Okay, now minus 0.92 minus 0.38i. Okay, now 0.38 minus 0.92i. And there we go. If you take any of these to the fourth power, you're going to get just I. Okay, let's solve this equation. So let's add this 4 plus 4i root 3 to both sides. So we've got, okay, now take the cube root of both sides. And we've got, so, okay, what are the three numbers that when you cube them, you get 4 plus 4i root 3? All right, well, let's so 4 plus 4i root 3. Okay, so let's get the radius. So, okay, 16 plus 16 times 3, 48. So that's 64. So the square root of 64. So we got 8. Okay, then the theta, the angle, if we do arc tangent of, so let's see, 4 root 3 over 4 is just root 3. So with the 30, 60, 90 triangle, okay, let's see. So tangent 60 is root 3, so 60 degrees. Now, whereas this number, it's in the first quadrant, so the angle is going to be 60. There we go. So now the radiuses of each of the three roots is going to be the principal cube root of 8 is 2. So 2, 2, 2. Okay. Now the alphas we've got, so 60 degrees plus 360 times k over 3. So alpha 1 is equal to 60 divided by 3 is 20. Alpha 2 and alpha 3 we've got, so add 120. Okay, so we've got cosine of 20 plus I sine of 20. We've got cosine of 140 plus I sine of 140. And then we've got cosine of 260 plus I sine of 260. So now let's put these in rectangular form. Can we, no, these aren't going to have nice reference angles. So, okay, that's no problem. We'll just use the calculator. So cosine of 20. Okay. All right, 1.88 plus 0.68i. Okay, now let's do 140. All right, minus 1.53 plus 1.29i. Okay, now let's see. Minus 0.35 minus 1.97i. And there we go. You take any of these numbers and you cube it, you're going to get 4 plus 4i root 3, which would satisfy this equation.